Monoidal categories and their representations. Lecture 1. Recap on categories. Let us start with a brief description of the structure of the course. The main book, which will be used during the course, is the book Tensor Categories by Ettinghoff, Gelacki, Nikšić, and Ostrich. And this book can be found at this location on the internet. The course will be divided into 4 major parts. The first one will consist of basic definitions and properties. The second one will mostly focus on tensor categories. The third one will be about module categories. And the last part will be devoted to examples. Each of these parts will consist of 4 lectures that will be followed by 1 problem session. Let us start our recap with the notion of a preadditive category. We denote by ab with capital A the category of all abelian groups. Definition: a preadditive category is a category which is enriched over ab. This means the following. If C is a preadditive category, then any Hom space in C is an additively written abelian group. Furthermore, the composition in C is a biadditive map. This means that if we want to compose a morphism F after the sum G plus H of 2 other morphisms, the outcome should be equal to the sum of the composition of F after G with the composition of F after H. And similarly for the second argument, if we want to compose the sum of G plus H after F, this should be equal to the sum of the composition of G after F and the composition of H after F. We note that this requirement of biadditivity is very similar to the property of distributivity between the usual multiplication and the usual addition of numbers. Also note that since we assume that each morphism space is an abelian group, it is non-empty and it contains the neutral element. And since our abelian groups are additively written, this neutral element is the 0 element. So each Hom set in our category contains the 0 element. Here are some examples of preadditive categories. The category of all abelian groups is a preadditive category. Similarly, its subcategory of all finitely generated abelian groups is a preadditive category. This is usually denoted by ab with little a. Next, the category of all vector spaces over some field is a preadditive category, and the category of all finite dimensional vector spaces over some field is a preadditive category. Similarly, the category of all modules over some unital ring is a preadditive category, and its subcategory of all finitely generated modules is also a preadditive category. More generally, any full subcategory of any preadditive category is preadditive. And it's a very fun exercise to construct with a full proof an example of a category that is not preadditive. Let us now recall the notions of additive categories and additive functors. Definition: an additive category is a preadditive category which has finite biproducts. This means that for any 2 objects x and y of any additive category C, there exists an object denoted x direct sum with y in C, and morphisms px from x plus y to x, so this is a projection onto x, the morphism py from x plus y to y, this is projection onto y, the morphism ix from x to x plus y, so this is the inclusion of x, and the morphism iy from y to x plus y, this is the inclusion of y, such that the following equalities hold. Projecting onto x after including y should be 0. Similarly, projecting onto y after including x should be 0. Projecting onto x after including x should be the identity on x. And projecting onto y after including y should be the identity on y. And finally, the sum of the including x after projecting onto it and including y after projecting onto it should be the identity on x plus y. Definition: a functor f from a preadditive category C to a preadditive category D is called additive if each map from the morphism set Cxy to the morphism set D f of x f of y, so the functor f consists of such maps for any pair xy of objects in C. So each of these maps should be a homomorphism of abelian groups. Remark: if both C and D are additive categories, then a functor f from C to D is additive, which means it satisfies this definition, if and only if it preserves all byproduct diagrams. This is also a fun exercise. Here are some examples. For any ring R, both the category of all modules over R and the category of all finitely generated modules over R, both these categories are additive. A negative example: a full subcategory of an additive category is not an additive category in general. The property of being pre-additive is inherited by full subcategories, but the property of being additive is not. An example of an additive functor, the identity functor on any preadditive category, is, of course, additive. Note that each additive category has finite byproducts. In particular, it has an empty byproduct, which is the zero object of that category. And so we can define the zero functor from any additive category to another additive category, which sends all objects of the domain to the zero object of the target category. This zero functor is also additive. Next example: tensor products are additive in each argument. And the home functor is also additive in each argument. More generally, any equivalence between two additive categories is an additive functor. Again, this is a fun exercise to realize why. Let us now recall the definition of a projective object. An object P of a category C is called projective, provided that for any epimorphism f from some object x to some object y, and any morphism g from our object P to y, there exists a morphism h from P to x such that g is equal to f after h. In other words, there exists some h such that the following diagram commutes. A typical example of a projective object is a free object. So, for example, free modules are projective, or free groups are projective in the corresponding categories. Another example: direct sums and direct summands of projective objects are obviously projective. And the usual characterization of a projective object: an object P is projective if and only if the functor of homing from this object preserves epimorphisms. The dual notion is a notion of an injective object. An object I of a category C is injective, provided that for any monomorphism f from any object x to any object y, and any morphism g from x to I, there exists a morphism h from y to I such that g factors as h after f. In other words, the following diagram commutes. So there is a morphism h from y to I, such that G factors as F and then H. So for example, an abelian group is injective as an abelian group if and only if it is divisible. In other words, multiplication with any positive integer n is a surjective map from this group to itself. For example, the additive group of all rational numbers, or the additive group of all real numbers, or the multiplicative group of all complex numbers are injective abelian groups. Second example, directly from the definition, the requirement in the definition of an injective object is obviously an additive requirement. So direct sums and direct summons of injective objects are injective. And dually to the notion of a projective object, here is a characterization of injective objects. An object I is injective if and only if the functor of hominin to this object sends monomorphisms to epimorphisms. So here this place is contravariant. So we start from a monomorphism, we end up with an epimorphism. Next, let us talk about K-linear categories. So let K be a field. Let us denote by K mod with capital M the category of all K vector spaces. Definition: a K-linear category is a category enriched over K mod. This means the following. If C is a K-linear category, then every Hom set in this category is a vector space over K, and the composition is a bilinear map. In other words, if we want to compose morphism F with a linear combination lambda G plus mu H, the outcome should be lambda times F after G plus mu times F after H. And similarly for the second argument. Directly from the definition, we see that any K-linear category is preadditive, and in particular, each Hom set in a K-linear category has 0 element. Here are some examples. Of course, the category of all K vector spaces is K-linear, and similarly, the category of all finite dimensional vector spaces is K-linear. The category of all modules over some associative K algebra is K-linear, and the category of all finitely generated modules over an associative K algebra is K-linear. The category of all projective A modules over an associative algebra is K-linear, and the category of all finitely generated projective A modules for an associative K algebra A is K-linear. And similarly to the preadditive categories, the property to be K-linear is inherited by full subcategories. Any full subcategory of a K-linear category is K-linear. Definition: a functor F between two K-linear categories is called K-linear, provided that each map from Cxy to D f of x, f of y is a linear map. And note that a K-linear functor is automatically additive. Let us now talk about finitary K-linear categories. Definition: a category C is idempotent split provided that for any object X in C and any idempotent E in the Hom space from X to X, there exists an object Y in C and two morphisms, morphism F from X to Y and a morphism G from Y to X, such that the composition of F after G is equal to the identity on Y, and the composition of G after F is equal to our idempotent E. So we have this diagram, we have X, Y, F from X to Y, G from Y to X, and E here is a loop on X. So the composition of G and then F should be the identity on Y, and the composition of F and then G should be our E. And this object Y is called the retract of E. So a K-linear category C is called finitary provided that each k vector space Cxy is finite dimensional. So each home set in C is a k vector space, and this vector space should be finite dimensional. Moreover, C should be additive, idempotent split, and it should have finitely many isomorphism classes of indecomposable objects. Remark: any finitary k-linear category has a Krull-Schmidt property in the sense that it has a unique decomposition of objects into direct sum of indecomposable objects. Of course, unique up to permutation and isomorphism. Here is a typical example of a finitary k-linear category. Let A be a finite dimensional associative K algebra. Then the category of all finitely generated projective modules over A is a finitary k-linear category. Indeed, for a finite dimensional algebra, we have finitely many isomorphism classes of indecomposable projective objects. Any projective object is a direct sum of indecomposables, and any home between two finitely generated A modules is finite dimensional. Therefore, a proj with little p is a finitary k-linear category. Conversely, theorem: let C be a finitary k-linear category with indecomposable objects x1, x2, and so on, xk. So we assume that this is a full and irredundant list of representatives of the isomorphism classes of indecomposable objects in C. Then the category C is equivalent to the category of finitely generated projective objects over the finite dimensional associative algebra A, given as follows. So the opposite of this algebra is the direct sum over all I and j of the morphism spaces Cxi, xj. So this set has the obvious structure of an associative algebra given by composition. Since all Cxi, xj are finite dimensional, this is also a finite dimensional vector space. So here is a sketch of the proof. If we have an object y in C, then the direct sum of all home spaces from all xi's to y has the natural structure of a right A module. This is because this xi is at the contravariant place of home. And so the structure is just given by composition. And if we take as y the direct sum of x1 and so on xk, what we will get, more or less by definition, is a regular A module. And this implies that for any y, you will get a projective module. It will be a direct summand of some direct sums of copies of the regular module. And then it's easy to check that this gives the necessary equivalence. Now let us talk about kernels and cokernels. Let C be a category and F a morphism from X to Y in C. Definition: a kernel of F is a pair consisting of an object K in C and a morphism G from K to X, such that the composition of F after G is 0, and the following universal property holds. For any morphism G' for some object K' to X, such that the composition of F after G' is 0, there is a unique morphism H from K' to K, such that G' factors as G after H. So here is a diagram. So we have our morphism F from X to Y. So K and this morphism G is a kernel. The composition of G followed by F is 0, so this triangle commutes. And now if we have any K' with a morphism G' to X, such that the composition G' followed by F is 0, there should exist a unique H from K' to K, such that G' is H followed by G. And cokernels are defined in the dual way. That's a nice exercise to do. Now we can define the notion of an abelian category. So we start with a pre-abelian category. An additive category C is called pre-abelian if every morphism in C has both a kernel and a cokernel. And now the definition of an abelian category. A pre-abelian category C is called abelian if every monomorphism in C is the kernel of something, and any epimorphism in C is the cokernel of something. Here are some examples of abelian categories. The category AB of all abelian groups is an abelian category. This is a prototypical example of an abelian category. The category of all modules over some unital ring is an abelian category. The category of all finitely generated modules over some Noetherian ring is an abelian category. As a special case, the category of all vector spaces over a field is an abelian category, and the category of all finite-dimensional vector spaces over a field is also an abelian category. A more general example, the category of all functors from a small category to an abelian category is an abelian category. Here the abelian structure is defined pointwise. Now let us recall the notion of a category with enough projectives. So let C be an abelian category. We say that C has enough projectives provided that every object in C is a quotient of a projective object. The first example, the category of all finitely generated modules over some finite dimensional algebra over some field has enough projectives. Also, for any ring R, the category of all R modules or all finitely generated R modules has enough projectives. The point here is that any module is a quotient of a free module, and free modules are projectives because they are free. The dual definition, we say that an abelian category C has enough injectives, provided that every object is a subobject of an injective object. So the first example is shared with projectives. The category of all finite-dimensional modules over a finite-dimensional algebra over a field has enough injectives. The second example is that the category of all R modules, where R is a unital ring, has enough injectives. However, the category of all finitely generated modules over some unital ring usually does not have enough injectives. Injective objects are usually not finitely generated. They're usually very big. Let us now discuss the notion of a simple object. Let C be an abelian category. An object X in C is called simple, provided that it is not isomorphic to the zero object, and any subobject of this object X is isomorphic to either X itself or to the zero object. Remark, it's very telling to compare this definition to the notion of a prime positive integer. Example, a simple module over some ring is a simple object in the category of all modules over that ring. Moreover, every simple object in the category of all R modules is in fact a simple R module. However, a small warning, simple objects in abelian subcategories of module categories sometimes might be given by non-simple modules. A telling example is if we take a simple R module and consider it just as an abelian group, it is usually not simple as an abelian group. And for simple objects, we have Schur's lemma. The endomorphism ring of a simple object in an abelian category is always a division ring. So now when we talked about simple objects, it's natural to discuss Jordan-Hölder series. So let C be an abelian category and X an object in C. A Jordan-Hölder series of X, which is also called a composition series of X, is a filtration of subobjects. So we start from the 0 object denoted by x0. This is a sub-object of x1, and so on, sub-object of xk, which is equal to x, such that each subquotient xi modulo xi minus 1 is simple. Note that not every object has a composition series in general. Moreover, if some object has a composition series, this composition series is usually not unique. But the length of this composition series is usually called the length of an object, and this is justified by the following Jordan-Hölder theorem. Given two different composition series of some object x, they have the same length. Moreover, the corresponding multisets of simple subquotients up to isomorphisms coincide. This we can use to define the notion of a length category. Let C be an abelian category. This says that C is a length category, provided that it is essentially small, and each object of C has finite lengths. A typical example of a length category is the category of all finite-dimensional vector spaces over some field. Another example is the category of finite-dimensional modules over a finite-dimensional associative algebra. Alternatively, the category of finite-dimensional modules over any associative algebra, not necessarily finite-dimensional. Or more generally, one can consider the category of finite length modules over a not necessarily finite-dimensional associative algebra. These all are examples of length categories. So here is a characterization of module categories as length categories. Theorem, due to Gabriel and Mitchell, let C be a k-linear category with the following properties. C is abelian, it has enough projectives, it is a length category, and it has finitely many isomorphism classes of simple objects. Then C is equivalent to the category of all finite-dimensional modules over some finite-dimensional associative algebra. To construct this algebra, let L1 and so on Lk be the finite complete list of simple objects in C, or of representatives of isomorphism classes of simple objects in C. So since C has enough projectives, we can then take the projective covers P1 and so on Pk of these simple objects. Then the algebra A is constructed as the opposite of the endomorphism algebra of the direct sum of these indecomposable projective objects. Next, let us recall the Eilenberg-Watts theorem in the restricted setup of finite-dimensional associative algebras. Let A and B be two finite-dimensional associative K-algebras. Let X be a finite-dimensional AB bimodule. Theorem: the functor of tensoring with this bimodule, this is a functor from B mod to A mod. So this functor is additive and right exact. Conversely, any additive right exact functor from B mod to A mod is isomorphic to the functor of tensoring with some finite-dimensional AB bimodule. So the left exact version of this theorem, the functor of homing from X, and this is now a functor from A mod to B mod, this functor is additive and left exact. Conversely, any left exact additive functor from A mod to B mod is of such form up to isomorphism. We know that the functor of tensoring with X is exact if and only if X is B projective, and the functor of homing from X is exact if and only if X is A projective. And finally, let us discuss the notion of a duality. Let A be a finite-dimensional associative K-algebra. Then we have the following two contravariant functors. The functors of taking the dual space homing into K The first functor is homing into K for the right K action, and this is the functor from A mod to mod A. And the functor of homing into K for the left K action, so this is a functor from mod A to A mod. So the composition of these functors in any order is isomorphic to the identity functor on the corresponding domain category. In particular, they both are contravariant equivalences between the corresponding categories, and these are called the duality functors. And the basic properties of these functors are that they both are exact, they swap projective objects and injective objects, and they send simple objects to simple objects. Okay, some problems and questions for today. Question 1, prove that a functor between two additive categories is additive if and only if it preserves the byproduct. Question 2, prove that any equivalence between two additive categories is an additive functor. Question 3, prove that for any field K, the category of all abelian groups is not K-linear. Question 4, give full details for the proof of the characterization of finitary K-linear categories. And question 5, give the definition of a cokernel and prove the uniqueness of cokernels up to isomorphism. Thank you very much and see you next time.